So what we're going to talk about today is really attacking hardware. Because attacking hardware is really fun. And there are many reasons that we might want to attack hardware. Maybe you want to extract secrets, right? We all have mobile phones. These mobile phones are typically carrying all of our data that's encrypted. And we can't even actually get the key. Often we have TPMs, we have secure enclaves, we have encryption chips that are actually that are storing keys that protect our data, which is nice, but we can't even get to that. Maybe you want to extract those keys. Maybe you want to create a device that can be compatible with something else. Maybe you want to modify your hardware. Maybe you bought something and you want it to run different type of code that the manufacturer doesn't want you to, but it's your device. I think you should be able to. And if you're interested, I mean, we'll go a little bit into this sort of stuff. I've been getting a lot of emails from people who say they've lost their dongle for their keyboard or mouse. And they're like, hey, can I make a dongle? And like, actually, yes, you can. You don't have to buy an entirely new keyboard, but that's actually what manufacturers make us do today. If you lose the USB dongle that stores the private key, the encryption key that's shared between your keyboard and dongle, you now have to buy a new keyboard. Now imagine if that happened with your car, right? Imagine if you lost your key and the manufacturer said you have to buy a new car. They can do that, right? There's actually nothing stopping them today that says they have to sell you a key. And really an overpriced key, right? These keys are what, $300 for what, I mean, Michael Osman has like a CC1110 chip. What is that, a couple bucks? I mean, that's basically what's inside of these devices. It's kind of crazy. So understanding this sort of stuff will just give you access to your hardware, to your software, the things that you own. Potentially things that other people own, but. So in this talk, we'll use the Arduino Uno because it's pretty ubiquitous, right? We're all at least familiar with it. It's a microcontroller, and we'll use that as a great example. Just to get an idea, who has performed side channel attacks before? Okay, awesome. And who has performed intentional fault injection? Okay, cool. All right. We'll go from the very basics. By the end of this, you will be able to do some really cool attacks with the hardware that you have in your bag. So what is a side channel, right? Let's just understand, and I think this is actually a really cool example, like being able to just listen to the ground and kilometers away, that's right, kilometers away, you can actually hear something coming, right? You can hear a horse coming. That's essentially a side channel. It's information that you're gathering from an implementation rather than the algorithm or system itself. And there's some really cool examples of side channels. This is from a video Mark Rober did, where he took a FLIR infrared camera that you can get for your phone. You just put it on the top of your phone, and then he went into a store. Someone typed their PIN code on the ATM, and immediately he took a photo. You couldn't even notice, and you can see thermally the code is 12345 because the heat 5 is the hottest, which means it was last hit by someone's finger. It's really cool. So this is an infrared side channel, for example. We have sound. There are many different papers and examples of using sound as a side channel. Berkeley used a microphone to track acoustic emanations from keyboards. Now, what they could do is after a few hundred keystrokes, after typing on a keyboard and having a phone simply nearby listening, they could tell what you're typing. Now, how does that work? Because you're just pressing keys, right? They all sound pretty similar, except they actually all sound very unique. Because of their location on a keyboard, they will produce the same sound. If you hit on your keyboard A versus S, those will have two different sounds. Now the amplitude might be slightly different, but you can use algorithms like dynamic time warping to actually figure out that these are the same. And if you know the language that someone is typing, let's say they're typing English, you know that the space is going to be used more than anything, so you immediately say, oh, this key is here, here, and here. It's used the most, so now you just have your word separator. Then you're just doing frequency analysis. Etoian Shrewdlu, what's the term? Some people know what that is. So that would be a sound side channel. There's visible light. The guys at Inverse Path, Andrea Barasani and Daniel Bianco at Inverse Path, they used a laser at DEF CON maybe many years ago, and they would bounce it off of a reflective portion of a laptop. And similar to the sound, the frequency analysis of sound, they're now doing this with mechanical vibration. And visible light. So the visible light that bounces off, reflected onto their whatever optical receiver that they had, they can then perform the same exact analysis and figure out what you're typing. And this could be visible. You could use infrared as well. I think I first heard about the side channel stuff with the NSA. Yeah, sorry about the URL there. But in the 60s, the NSA developed Tempest attacks. And Tempest was when they found that CRT monitors are constantly emitting a ton of electromagnetic radiation. So from a side room, they could have an antenna set up and see what's happening on that screen because of the radio frequency emanations that are coming off of here. I mean, this stuff is just like absolutely amazing. And I think what's cool about all of these attacks, at least the ones that I'm sharing with you, is that we can all do these, right? This doesn't require nation state funding. This doesn't require ridiculous computation. This is stuff that we can do ourselves. Ultrasound, this is super, super cool. The University of Tel Aviv was able to take a standard mobile device, put it next to a laptop, and listen to the ultrasound coming off of a computer. Why is your computer even producing ultrasound? We can't hear ultrasound, but your computer is producing it constantly. The capacitor is going through something called electrostrictive effect, where basically they're moving due to an electric field. They're physically moving, the capacitors inside, and they're moving against your PCB. They're happening fast enough that it's producing ultrasound that you and I can't hear, but that a standard microphone in any mobile device can actually listen to. Then they're using that to perform analysis on what instructions are being run. Because if, say, you're encrypting something with RSA, with a 4096-bit secure key, well, that's going to take a different operation if you're using a 0-bit versus a 1-bit in your key. You're actually doing, I think, something like a multiplication versus a multiplication plus some other operation, maybe modulo. And because of that, you can then do timing and power analysis just by that ultrasound. And having just a simple phone, you can record that information and extract the full key. I mean, it's absolutely crazy. There's power attacks. So that was ultrasound. We have power. All these physical phenomena are all leaking all this information all the time on everything we use. It's crazy. You can measure power to discover leakage. Inverse path guys also did a demonstration where they could plug into a ground on a circuit and then pick up information or noise that was coming off of a keyboard somewhere else on the same circuit. And they could figure out what you're typing. Or you could do power analysis to extract keys like we saw with ultrasound. This is terrifying. This is a bag of potato chips. If you see this, watch out. Someone could be listening to what you're saying. When MIT was in a soundproof room, they did a demonstration where they put a bag of potato chips in a soundproof room with soundproof glass. And then on the outside, they took a DSLR camera, looked inside of that room, and recorded the video at standard 60 frames per second. And they were able to then extract sound that was being stated, what someone was saying inside of the room. And they were doing that by looking at sound as vibration of air. So that air is then vibrating against the bag of potato chips. And then the potato chip slightly moves, right? Not enough that you or I could see, but a computer could easily see it. And what's kind of incredible is that hearing is at 20 to 20 kilohertz, right? 20 hertz to 20 kilohertz. But they were able to use DSLR's camera is not actually taking 60 frames per second. It's taking many, 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 many pixels per second, right? So if you're watching these pixels, that's actually changing many times, more than 60 frames per second. And they're able to convert that visible light or that motion back to sound and hear what was in the soundproof room via light. It's crazy. And time. Time is an excellent side channel. So we'll use that as a simple example. So again, we'll look at the Arduino Uno. We're all familiar with Arduino Uno for the most part. Really, the brains of the Uno is the ATmega 328P. And that's a standard microcontroller, AVR architecture. We'll take a little bit deeper look here, but a clock is pretty much driving everything on most processors, most microcontrollers. Excuse me. So you have a ton of sequential logic that's controlling flip-flops, flash, RAM, FIFOs, all this stuff. And we'll take a simple program. This is very basic. We create a password, and we ask the user. Let's say we're the software developer writing the firmware for this chip. We ask for a password. The user enters their password over the serial, and we validate, is the password equal to the guess? We're using the string library here, so that will handle things like EqualEqual. So what's wrong with this code? And I think the answer is nothing is actually wrong with this code. Unfortunately, there are a ton of side channels that can exploit this code. So we're going to be revisiting this code a couple times now. So if we look at this, we see password equals guess. So how is it validating that the password we entered is Hunter2? Well, we can take a look at what EqualEqual does. And if you pull up the Arduino or AVR core, if you look at Arduino, this EqualEqual is actually defined in wstring.cpp. So you can look at your Arduino source code, pull this up, and you can see what's happening. This is a snippet of the code, but this is really the critical part. Here we're saying EqualEqual gets overloaded and calls this equals function in your string class. And then equals is taking basically your two things and saying, are they equal? It's doing that via string compare. String compare is part of the libc library. So if we look at libc, then we can look at how that's being done. So looking at libc, string compare, all we're doing is we're looping through a string, character by character, and seeing are they equal or not. Very simple. And then if we compile that down, we actually get assembly. And if we look at that, then it's again very similar. We are just now going byte by byte through the password. We're starting at, for Hunter 2, we start at H, and then go to U, validate that each character is the same. And if any mismatch, then we break. We branch and we return. That's pretty cool. That all makes sense. But what's interesting here is that, again, we have this clock that's controlling everything. So the clock is fetching instructions from flash. It's putting an instruction register, and then we're doing this validation byte by byte. Now, all of this takes time. A clock really takes time, right? And that's the idea of a clock. So what if we measured that time? This is a very, very simple attack that you can perform today with virtually any equipment. I mean, all you need is an Arduino to actually perform this type of actual attack. So if we type, let's say, HAK versus GAK, there will be a difference in the timing. The amount of time it will take is going to be slightly longer for HAK because the H was correct. How much time? Well, I measured it with a Samy logic analyzer. We see about 3 microseconds. 3 microseconds is something like 333 kilohertz. So if you have something that's running at, say, a megahertz, like an AT-Tiny internal oscillator, you will be able to measure this type of difference. And all you have to do at that point is then go through all of your characters. So instead of brute forcing the entire key space, you're only brute forcing the first character and saying, oh, this character takes slightly longer than all the other characters, and now you know what your first character is. Then you go onto your second character and you perform the same loop. This is absolutely incredible. This is a very simple timing attack. It's been known for a long time, but it's something you can do on devices today. So very exciting. And you can use side channels to do a lot of other cool stuff. For example, AES and RSA key extraction. So if you have some sort of key that's stored inside of your device, maybe it's a mobile device, maybe it's some sort of console, maybe it's a computer, you can use these same types of attacks and using side channels, using the various side channels that we mentioned before, and hopefully others that some of you will create and think about, you can extract all sorts of things. Some of the tools that I would suggest that I've used, the Chip Whisperer is an amazing tool from Colin O'Flynn. It's inexpensive, has an FPGA built in, and he's created amazing videos, tutorials online, so much information that you can use online to really learn how to pull off these attacks. And he's doing a great job of really explaining how a lot of these things work, as well as providing open source tool chain, open source hardware, open source software that you can perform all this stuff. And he's using real targets, which is another thing I really appreciate, is that he's grabbing actual chips that many people are using and demonstrating how you can actually perform those attacks. If you want to start small, if you want to start on maybe a cheaper scale, you can buy the Ice Stick. It's $25 for an Ice 40 FPGA. And you can perform these types of attacks with an Ice Stick. Very cool stuff. An oscilloscope, right, I use Rigol. They're very inexpensive. Again, these are also starting maybe $200, $300, and you can get something extremely powerful, really cool. Samy logic analyzer. Samy is on the more expensive side of logic analyzers, but I love the software. But there's plenty of other logic analyzers that you can use. There's open source software like SIGROC that you can use. And you can start doing these types of really cool attacks. Now, a side channel is one area. But there's also fault injection, and I think we talked about we're interested in intentional fault injection, where we can extract secrets or modify a device to do something interesting. Jasper Van Woudenberg had a cool example in one of his talks where he was talking about fault injection, and he used this as an example. He used a pinball machine, and a cool fault injection attack on a pinball machine is tilt. Right, if you can tilt this, you can make the ball maybe go somewhere that it shouldn't, even though normally you're only supposed to be using, let's say, those flappers on the side. So what are some types of fault injection attacks? And if we look at all the stuff that we did with the side channel, we can do the same thing with fault injection, but now instead of receiving, we're more transmitting. So some cool examples. There's an interesting example of, there's plenty of examples of cracking safes using fault injection. This safe, you can actually do the same type of side channel analysis. You can see how long does it take if I enter a 1111 versus a 2111. If the 2 is correct, then it will typically take a little bit longer because now it says 2 is correct. I'm now going to go back and check, is this next character correct? So it will take a little longer. However, this specific safe, has some protection mechanism against that. So every time that you actually enter a pin, an incorrect pin, it then writes to EEPROM and says, oh, this person performed an incorrect pin, and I'm going to have a timeout. It's kind of like on your phone, if you're trying to enter the wrong code over and over and over again, it will start to back off, or it'll have a time delay. So what they did was they said, there's also a reset attack where you can then reset the chip so that it doesn't remember, oh, this person just tried 3 incorrect codes, make them wait 10 minutes. However, they thought about that and said, no, we're going to write to the EEPROM and say, this person just did an incorrect code, so even if they try a reset attack and they try to reset this chip, we're going to know that, and we're still going to know exactly how many times they did that. But the interesting thing about EEPROM, it's electrically erasable programmable read-only memory, which makes no sense because how is that read-only? We should just call it something else. But okay, the way EEPROM works is that in order to write to it, you must first erase it. So if you can accurately time that, and let's say you enter an incorrect code, so now that EEPROM turns to 1, and then you enter another incorrect code, and now that EEPROM turns to 2, and now you're about to enter another code that's about to lock you out for 5 minutes, well, if you can time it accurately, and which you can, all of this stuff is time dependent, then you can say, I am going to wait for the EEPROM to start first erasing that 2 to a 0, and then reset. And before it has the chance to then program, you've now reset that counter and you can perform your attack again. And then you brute force, you perform the same side channel attack or timing analysis that we did initially, and you've now cracked this UL security listed safe. There's an excellent, I've linked to the video. Someone else performed this attack at DEF CON. Very cool, and just really interesting to see the types of faults that can be done in conjunction with side channel analysis, power analysis, time analysis. So just to talk about some of the other cool physical phenomena around fault injection. A really cool paper on attacking drones and controlling drones using ultrasound. So all of our drones, they have IMUs. Right, these are accelerometers, gyroscope, magnetometers that are measuring, okay, where am I? The nice thing about a drone, the reason it's so cheap is because there's really just a little microcontroller and an IMU that's controlling everything. It's saying, oh, that's unfortunate that my left front wing is really heavy, or propeller. I'm going to account for that because I see my gyroscope's telling me, oh, I'm going down. So the CPU will then say, no, let me add some more power here and spin up. And that's how you get that accuracy. But a lot of these MEMS, accelerometers, and gyroscopes have resonant frequencies that if you hit with ultrasound, you can make the device believe it's somewhere else, or it's in a different position than it actually is. And you can now control it to do something else. There's temperature. Temperature is super cool. There's the cold boot attack. If we take a look at RAM, let's say when you log into your computer, you're typing in your password. And your password gets stored in memory so that it can decrypt your hard drive, because all of our hard drives are encrypted today. And that is stored in memory, and then maybe you close your computer, but the key is still stored in memory. Now, no one should be able to actually access your data, because when they open it, they still have to re-enter a password to actually log in. But your key is in memory, so can we pull that off? The problem is, I could try to pull your memory out of your computer, but memory is volatile, right? It will disappear in a second after pulling it out. But inside of memory, if we're looking at DRAM, DRAM is really just a grid of transistors and capacitors. A single transistor and capacitor is the capacitor is holding a bit of information. It's either a 1 or a 0. And that is constantly being refreshed. Now, a capacitor is really just holding, it's just, if there's voltage, there's really just a difference of electrons between the two sides, right, between the two poles. Now, electrons will, if you remove power, that will leak, and you'll have, eventually they will equalize and have no voltage on them. But if you cool it down, now you are now actually cooling down that capacitor and making it take much, much, much longer. So you can use canned air upside down, get your memory to be really, really, really cold and perform what's called a cold boot attack. You can then pull that memory out, and you have 1 or 2 minutes where you insert it into another device and then use just the RAM and pull all the contents out, extract your key, and now you've pulled the keys out. Bunny has done a really cool demonstration with resetting PIC 18F chips, the fuses on them. We don't actually have fuses anymore, just FYI. They're actually E-fuses. So the fuses in our microcontrollers are resettable. Fuse is not actually resettable, right? If you break a fuse, you have to replace it. These are E-fuses. So what these are doing is, in the PIC, for example, these are set via ultraviolet light. or reset via ultraviolet light, which is how you can actually reset the fuses. So what Bunny did was he had a chip. It had firmware that he wanted to extract out of there. But there was a fuse set that said, no, I'm not going to allow any debugger or external device be able to extract any firmware. So he opened up the chip, he drilled inside of it, he covered part with tape, with electrical tape, and then shown UV light on the rest to reset the fuses, because it's UV light that resets them, and was able to then connect and extract information. So ultraviolet light, temperature, visible light. Just last week, 2 weeks ago, lightcommands.com came out demonstrating some sort of photoacoustic effect, which I don't understand. Someone will have to explain to me. But essentially being able to use a laser, hit a microphone, and for some reason, that laser light turns into sound. Someone please explain that to me later. But here's the link. So let's just go back to our code here and see what we can do. Can we do something cool here? What's wrong with this code? Nothing. Except, how does this happen? So we looked at password equals guess before, and that was the string compare that we saw. But if we take a higher level look, we can take a look at the assembly instructions here. So we have our call string compare at the top, which was when we're comparing our function. Now that itself takes some time, and once assuming that's true, then we will end up skipping this branch instruction. If it's false, if our password is incorrect, we will actually perform a branch and then end up at this other location, this 3B7, and we will skip the good job message. Well, what's really interesting is with fault injection, you can now skip instructions. Right? There are techniques that you can use, such as voltage glitching or clock glitching. Here we can do essentially a voltage glitch, and all you're doing is you're removing voltage from the chip, from part of the CPU for just a moment as it's performing that instruction. Instructions take time, so you can perform a clock glitch where you send a clock. Let's say your Uno expects maybe a 16 megahertz clock, and if you can glitch, it's going to do everything on a rising edge. So if you can say send a rising edge, but not give it the time it needs to execute everything, because everything is sequential logic here, you can then skip that instruction. This is actually extremely, extremely easy. You'll all be able to do this today. And it looks like this. Basically, you are giving a voltage. Typically, you want to give a very low voltage. And traditionally in these attacks, at least in voltage glitching attacks, you want to remove any bypass capacitors to prevent decoupling. So normally you have a voltage regulator, and that's applying your power to your chip. And then we have some bypass capacitors. So if the regulator can't provide enough power for some peak moment, those bypass capacitors will help you. But this is essentially a tilt, right? By removing the voltage for just a moment, just an instruction, and removing the bypass capacitors so the CPU starves, you will then skip an instruction, assuming that your glitch voltage is low enough and your pulse width is long or short enough. You will have to play with this stuff, but the nice thing about devices like microcontrollers and FPGAs is that you can program them and you can make them do really cool stuff. So fault injection, we'll just look at some of the tools that we have. We all have this thing in our bag, which is pretty sweet. So we have an FPGA that we can perform these types of attacks today. Again, Chip Whisperer, excellent for fault injection. As I said, the Ice Stick or the Ice 40, another inexpensive $25 device that you can perform these types of attacks. I'm not going to do a lot of FPGA. I'm going to go to a lot of more FPGA talks and learn from other people here. And there are a ton of FPGA talks this year, which was a surprise and a very pleasant surprise. We'll look super briefly at some basic code, something that sort of like broke my brain when I started looking at FPGAs and Verilog or HDL, and this code is running in parallel. So x is equal to 1, y is equal to x plus 1. You'd expect y is equal to 2, but y is not equal to 2 until the next instruction because all of that stuff is running in parallel. So that's pretty interesting. And why is an FPGA, I was also sort of confused, why is an FPGA a field programmable gate array? How is it any more programmable than, say, my microcontroller, right? How is it more programmable than my Arduino? Except for the fact that in your, say, Uno or your ATmega, you have all of these different blocks, right? You have your UARTs, your SPI, your RAM, your CPU, your ALU. All these different pieces are taking transistor space or silicon, right? They're taking silicon space that you can then replace with something else. Maybe you wanted to make a rainbow table. Maybe you wanted to generate rainbow tables instead of having SRAM. Maybe you wanted to make rainbow tables instead of having UART or SPI or I2C or USB. All of these devices can be reconfigured to do really interesting things. And the nice thing with FPGAs when performing these types of attacks is that you get extremely precise clock. So when you're trying to do very precise attacks, you can, the FPGA will be very beneficial. However, you don't need to use an FPGA. One thing that you will need for something like this is a fast multiplexer. Chris Grolinski found this guy, the MAX 4619, which allows something like 10 to 20 nanosecond times to switch, which is absolutely incredible when you're talking about muxes. So if you're doing something like switching a clock from your normal clock to a different clock, then you can use the mux. Or if you're switching from a voltage, say your normal 3.3 volts or 5 volts, and you want to give 0.2 volts to this device, then you can use this mux. And this will switch for 10 nanoseconds and then switch back. And that will be able to deplete your microcontroller with the power, for the power to skip a specific instruction. Teensy. Okay, the new Teensy 4 is just a beast, right? 600 megahertz, but you can use even a Teensy 3 to do these types of attacks. So originally I was using the FPGA to do a lot of these attacks, and I just wondered, like, can I use a Teensy? Because that's something that many of us have, and the answer is yes. I'll provide a bunch of code so you can perform fault injection, side channel analysis using a Teensy in the 3 series. So one more example that I think is pretty interesting. What's wrong with this code? Nothing, except for the fact that the password is right here. The password has to be stored somewhere, right? It might be hashed. In this case, it's not hashed, so that is an issue, and you wouldn't want to, typically you want to hash password if it's in your code. But how can we talk to our chip? Maybe we can extract that password. So to actually extract a password, we can use something like a debugger. So with Uno, you can get something like the Atmel ICE, you can use a JTAG or a Segar or a JLink, things like that to basically communicate with the chip. The chip has a boot ROM, it has debug wire, and it has these features that allow you to actually access the flash inside and extract that. Now, that itself is not an attack. These are intentional, right? These chips are designed so that you can access the data inside and verify whether it's correct or not. Except for the fact that they also have these features called lock bits or fuses. And these will allow the designer to lock their firmware, their memory, and the idea is to prevent other people from being able to access the data. So if we look inside of here, part of this stuff is the debug wire and the programming for using parallel and SPI. Well, all of this is also sequential. All the on-chip boot ROM, the boot ROM itself that's protecting your chip is also sequential logic, right? It is running essentially clock cycle after clock cycle after clock cycle. So why can't you glitch this as well? This is an example from Chris Grolinski's setup. Several years ago, he demonstrated bypassing the NXP LPC bootloader, which is used in a ton of chips. It's used in various locks, all sorts of interesting things. And essentially by removing the bypass capacitors and performing a voltage glitch, you can then bypass the boot protection that actually protects the flash if you're trying to, say, release a product and store some keys, store some secrets, store some firmware that might have other faults, might have vulnerabilities in it. You can bypass all of that with a simple voltage glitch. I hope many of you start getting into this. I'd be happy to chat after. There's so much in this area to be done and so much to talk about, but we have limited time. I think one thing that I've been playing with recently, which I think is pretty interesting, is really evading tampering. So normally with all of the attacks that have been done so far, you've had to modify your board. You've had to, let's say, remove the lock from the door or open the safe. Well, that's convenient. I mean, you have to open the safe and then remove bypass capacitors to perform these attacks, which doesn't really make sense. So I've been working on how can we actually evade tampering. So normally you either have to modify the crystal and actually provide your own clock, or you have to remove the bypass capacitors around the microcontroller because the capacitors are storing all this extra energy. Well, what we want to actually do is a truly non-invasive attack. So far we've been talking about primarily non-invasive attacks where you don't actually have to modify the IC itself, but really you do have to modify the PCB. So I think that is somewhat invasive if you're actually removing screws and you're breaking plastic and you're sitting outside of someone's hotel room trying to with a PCB out there. So non-invasive attack, a very simple mechanism to perform a truly non-invasive attack is through a capacitor. Just by adding a capacitor to, say, your voltage glitch line and ground, what you're going to do is you're going to add a ton of capacitance to the voltage glitch. So let's say your glitch is 0.2 volts, and your device expects 3.3 volts. So you're normally running at 3.3 volts, and then for 20 nanoseconds or 200 nanoseconds, you're going to give it 0.2 volts. The problem is those bypass capacitors inside of the device, which you haven't touched, are going to now keep that 3.3 volts steady for just a little bit before they deplete, except for this capacitor, which if you use a large capacitor, say a 470 microfarad capacitor on the outside, well, that is actually going to deplete, that is going to deplete your bypass capacitors for you before the MCU has much time to essentially execute any instructions. And you'll be able to then bypass security through without any modification. Happy to talk about this further. And I will have a bunch of code here that you can check some stuff out, and happy to chat afterwards. Thanks so much.